Welcome to this lecture on signal analysis, where we dive into the fundamental operations of convolution and correlation. These are not just mathematical exercises, they are the bedrock of how we process signals, understand systems, and measure similarity in everything from radar to audio processing. By the end of this session, you'll understand exactly how to define them, why they're different, and how they define the behavior. We often talk about signals interacting with each other. Convolution tells us how a system modifies an input signal, essentially blending two functions together. Correlation, on the other side, is our mathematical tape measure. It tells us how much one signal resembles another as we slide them across time. Let's start with the formal machinery of convolution. Formally, the convolution of two signals, x of t and y of t, is defined by this integral. Notice the argument t minus tau. This represents the second signal being flipped and then shifted by time t. The result is a new signal, z of t, which captures the overlap of these two signals as they pass through one another. It is the essential operation for characterizing LTI systems. To visualize this, consider two simple rectangular pulses. As they overlap, the convolution product grows linearly, peaks when they perfectly align, and then decays as they move apart. The result of convolving two rectangles is a triangle. This simple geometric transformation is a classic example of how convolution smooths or spreads information. Convolution has several powerful properties that make it easy to work with. It's commutative, meaning the order doesn't matter. It's distributive over addition, and notably, the Fourier transform of a convolution is simply the product of the individual transforms. This convolution theorem is why we often prefer working in the frequency domain. It turns a complex integral into basic multiplication. Now, let's talk about correlation. The intercorrelation function measures the similarity between two signals. The formula looks strikingly similar to convolution, but look closely at the argument of the second signal. It's t plus tau. There is no flip here. We are simply shifting one signal and checking for a match. When we compare a signal with itself, we call it autocorrelation. The relationship between the two is simple. Cross-correlation is equivalent to the convolution of the first signal reversed in time with the second signal. So, if you can compute a convolution, you can compute a correlation. You just have to flip one of the inputs first. This connection bridges the gap between system response and signal similarity. Correlation has its own set of rules. Unlike convolution, intercorrelation is not commutative. The order of signals changes the result's time shift. However, autocorrelation is always symmetric. It's an even function. This symmetry reflects the fact that a signal is always most similar to itself when there is zero shift. One of the most important values in autocorrelation is the peak at zero shift. Rxx of 0 represents the total energy of the signal. We often normalize this to get the autocorrelation coefficient, which stays between -1 and 1, giving us a standardized measure of resemblance. With these tools in hand, we can define linear time invariant, or LTI systems. A system is linear if its response to a sum of inputs is the sum of its responses to each input individually. It's time invariant if delaying the input simply delays the output by the same amount. Most real-world systems, like circuits and filters, are modeled as LTI. An LTI system is completely and uniquely defined by its impulse response, h of t. This is simply the output you get when you hit the system with a Dirac delta pulse. Once you know h of t, you can find the output for any input signal x of t using, you guessed it, the convolution product. Mathematically, this means y of t equals x of t convolved with h of t. In the frequency domain, this relationship becomes even cleaner. The output spectrum y of f is the product of the input spectrum and the system's transfer function, h of f. This simple multiplication is the core of filter design and signal reconstruction. To wrap up, convolution describes how signals interact with systems, while correlation measures how signals resemble one another. We've seen that LTI systems are characterized by their impulse response and that the convolution integral is the engine that drives their output. These concepts are the foundation of everything that follows in signal processing. Thank you for joining this session on convolution and correlation. Keep practicing these integrals, and you'll soon see these patterns everywhere in the world of signals.